want to acknowledge these people. So this project was done together with them. So recently there has been some interest in studying what's called non-equilibrium dynamics in neuroimaging data. And with neuroimaging data, I mean either functional MRI or extracellular electrophysiology, as recorded with EEG or ECOG or LFTs, or MEG even. So large-scale signals. And so-called non-equilibrium measures, they have been applied in several studies to characterize different brain states, like anesthesia or sleep. And so what I want to do in this talk is first to explain what is meant by non-equilibrium dynamics in this context. And second, I want to tell you what I did in this study, and that is a way of detecting non-equilibrium dynamics in an invariant way. That means independent of the coordinate representation of your data, and why that is important. And then I will have a brief application to ECOG data. So here's an example of one of these recent studies. And this is the result of this non-equilibrium analysis. And in the first part of the talk, I want to kind of explain what these pictures mean in a more formal way. So the first step is that, so you have recorded brain activity. So suppose you have n brain regions. So we have n time series. And the first step is that you treat these time series as a realization of a stochastic process, right? Because otherwise you cannot do much. And so we have here an n-dimensional stochastic process that is described by some probability distribution that depends on the sorry, this should be n-dimensional, and it depends on time. So just a time-varying probability distribution on n-dimensional space. And of course, such a distribution can have many different dynamics. So a large class of models to describe these dynamics, so-called stochastic ordinary differential equations. Yeah, so we assume that this stochastic process is generated by an equation of this form. So it's just a differential equation which has some deterministic part. So this is just an n-dimensional vector field, A. And then here we have white noise coming into the system. And that enters the system through this function, diffusion function. So, and that diffusion can depend on the state of the system. Then if that's the case, then this is called multiplicative noise. And if B does not depend on X, it's called additive noise. Yeah, so if you have a system of this form, the dynamics of the probability distribution is governed, is described by a Fokker-Planck equation. And that is, so that's a partial differential equation for the probability density. So here you see the rate of change of the probability density to time is some sum of the partial derivatives of a function J. And this function J is called the probability current. So in this analysis, I will assume that the system is in steady state. And that just means that the probability distribution does not depend on time. In practice, that's relevant because if the system is in steady state, then its behavior is a stationary stochastic process. And then you can actually do some statistics. And of course, brain activity is not really stationary, but on the time scale of, say, well, in resting state, it's pretty stationary on the time scale of minutes. So this is a reasonable approximation. And if you have a system in steady state, then this probability current is also static. It does not depend on time. And from then it follows that, so if this is zero, then this is zero. So this means that the divergence of the probability current vanishes. So a system is in steady state if and only if the probability current vanishes. if and only if the probability current is divergence free. And here's a picture of what that means. So if you take a point x in the state space, and if the divergence is negative here, so the sum of the partial derivatives, that means that locally you have a kind of inward flow of probability towards that point. So you just should think of probability as some substance with a total mass 1. It can flow into a point, so this is like a source of probability. And if the divergence is positive, you can have an outflow of probability. But locally it leaves a point. And so if the system is in steady state, it means there's no local buildup or dispersion of probability. But you can have something like this. Yeah, so, but here you can see that if the divergence of the current is 0, it does not mean that the current itself vanishes. Right? Because here you see how you have a local flow. And so because it can happen that locally you have a flow. And this is exactly a definition of non-equilibrium in this context. Yeah, so a system is in non-equilibrium. It means that this current vanishes for every point x in the state space. And here you have an example of one of these studies on EcoG data, where they applied, there's the principal component analysis of the data. So they have two components. And then they reconstructed this probability flow. And here you see how it looks in a awake state and in a sleep state. So here you see, for example, that this system is not in equilibrium, because there's a circulation of current. And apparently there's some differences, some difference between these two states. Okay, maybe a simple example. So if you have a system which has linear deterministic dynamics and additive noise, then you can show that the probability density of the system is Gaussian. Yeah, so it has some covariance matrix sigma. And the probability current has this form. So let's make some comments about this. So first is that here you see that this probability current is proportional to the probability density. So the current is stronger when you have places in state space where you have a high likelihood of observing the system.
Excuse me.
Yeah.
Do you need a pointer?
Oh, maybe that's good. Thank you.
Does it work?
Oh, that's good.
It works.
No, because it's a
Oh, the screen doesn't work. Oh, sorry.
Sorry. And the second thing you see is that this current vanishes if and only if this term is 0. And so, for example, if sigma is the identity matrix, so B is the identity matrix, then the current vanishes if and only if A is symmetric. Yeah, so non-equilibrium dynamics has to do with the asymmetry of this deterministic dynamics. Another observation is that if you calculate the inner product between the probability current at some location and the gradient of the probability density at some location, it's 0, so they're orthogonal. So it means that in every point in state space, so these are the contours of the probability density, the current is always orthogonal along these contours. These are just different examples of different sigmas. The probability always flows like this. Okay, so this was one characterization of non-equilibrium dynamics, but there are several equivalent characterizations. One of them is the following. So a system is in non-equilibrium if and only if the probability of observing some realization of the process is different from the probability of, it should be a minus t, the time reverse process. Yeah, so if they don't have the same likelihood, then we say the system is irreversible. And in practice, I think this is from the ECO study, how they do this in practice. So you have a time series, and you compare it with the time reverse time series, and then you look for differences. That's how you can detect this irreversibility from observed time series. So you don't have to fit actually a stochastic differential equation to the data, although other researchers have done that as well. You only just need the observation, the observed behavior. Okay, so this was a bit of background about non-equilibrium dynamics. So what I'm interested in this study is to detect this in a way that does not depend on the coordinates you use to represent your data. And why is that important? So our observed signals are actually so n-dimensional signals. They are related to the current source density. So that's actually a true brain activity. So this linear forward operator. It's called the lead field. Yeah, and this is true for EEG and ECOG and even also for LFPs. You have volume conduction. So the CSD is just a scalar field on the cortex. So X is a continuous space. And what you record at a single electrode, say electrode I, is just a weighted average of, in principle, all activity throughout the cortex. And so this L, this forward operator depends on the geometry of the cortex and the different tissues and their electrical conductivity, but also on the type of electrode and, for example, the reference scheme, the montage that you use for the recordings. So if you change the reference scheme, you get, in principle, different signals with different dynamics. However, here you can see that this forward operation is linear. So here you have time t, and here you have also time t. And actually, Kees Stam over there, he was one of the first to exploit this fact to assess functional conductivity in sensor space in a way that's robust to volume conduction. Because you can do this by exploiting the latency structure of the signals. Yeah, right. Because this is instantaneous. If you have no latencies here, no latency structure, then you cannot have a latency structure here. So that's the phase lag index. And the same is true for non-equilibrium dynamics. So if the underlying system, so this current source density is in equilibrium, then the sensor signals are also in equilibrium. So you can detect non-equilibrium dynamics on the sensor level, but of course it's distorted because the CSD is infinite dimensional and you project it to n-dimensional space, so you get some distortion. That's where this invariance comes in. Yeah. Ideally, what you want is that your sensor analysis does not depend at all on the lead field. But that's not possible in general, right? Because currents are much higher dimensional than your sensors usually. Well, depending on the experimental paradigm. For example, in resting state. So what happens geometrically? So you have an infinite dimensional space where the current source density lives. That's the brain activity. And the forward model projects this to a subspace, signal subspace. And that projection, well, you have to deal with. You cannot do anything about. But what you can do is want to make sure that the way this vector is projected to this subspace does not matter. So in other words, suppose you project it into two different ways on this blue subspace. If you analyze this projected data in a way that is invariant under linear transformations within the subspace, then you are not sensitive to this variability. But that was the idea that if you, and this not only applies to non-equilibrium dynamics, but to analysis of sensor signals in general, even LFPs. If you do it in a way that is invariant on the linear transformations, then you remove some of the variability in lead fields across session and subjects. But of course, you cannot remove all variability because, of course, you have two lead fields, L and L accent. If they span different subspaces, then you cannot just transform this one to this one by an n-dimensional transformation. So this only works if they have the same row spaces. But anyway, that's the idea. That's why invariance is important. So the question that I asked here is, how can we detect these measures? But how can we find invariant non-equilibrium measures? I want to have all of them. I don't want to have one. I want all of them. Really. So now, so mathematically, let's see what this means. So we have an n-dimensional stochastic process observed, and now in discrete time. And we look at the covariance function of these signals. So that is sigma at lag tau is the covariance between the covariance of x of t and x of t plus tau. Yeah, and here we assume stationarity by defining this in this way. And the idea is that in this study we only exploit the second order statistics of the signals to construct invariant detection measures. To keep it simple. So if this underlying system is in equilibrium, then this implies that the covariance matrix covariance function at lag tau is the same as at lag minus tau. It's time reversal asymmetry. And that is just the sigma tau transposed. Yeah.
Does it mean that you're already assuming that your invariant measure is a product of Gaussians?
No, I don't assume anything about Gaussianity.
But you are only looking at the second moment.
Yeah. So, okay. So I only exploit the second order statistics of the signals. It doesn't mean that the signals have to be Gaussian.
But your model is.
No. The underlying model does not have to be linear. It's only if you have a nonlinear model, then the higher order moments, lag moments, they contain additional information about the dynamics, which we don't exploit. No, it's not an assumption. It's just we only exploit second order statistics. Right? Yeah. So if the system is in non-equilibrium, let's put it in a different way. If we see asymmetries in this covariance function, then we can infer that the system is in a non-equilibrium. Okay, and this is what, for example, Gustavo Deco did with his irreversibility measures. Look at the asymmetric part of the covariance function. But I want to have it in an invariant way. So let's collect these covariance matrices in an M tuple. We have an M tuple of n by n matrices. And we are looking at linear changes of coordinates in this. Yeah, so A is an invertible n by n matrix. And that induces this transformation on this tuple. Yeah, so all second order statistics is now captured by this matrix tuple. And this matrix tuple transforms in this way. So this is called this is a joint this is a conjugation. So what we want is so let's see, we're interested in a function that depends on the sigmas, so some measure or biomarker, and that is such that it's invariant under this transformation for all invertible A. And I also want that if the sigmas are symmetric, so meaning the system is in equilibrium, I want the measure to vanish. That's what it means to be a non-equilibrium measure. It vanishes for equilibrium systems. So this is what we want. A bit more formally. Okay, so we have to, let's make it a bit more formal to see what happens mathematically. So if these tuples, they are part of some vector space of M tuples, let's call that sigma. Then in this space we have a subspace of symmetric tuples. These correspond to equilibrium systems. And these functions that we're interested in, so these biomarkers, F, we assume them to be polynomials. So our functions will be polynomials in the entries of these matrices. Yeah, so this is a ring. Algebraically, this is a ring. It's called a polynomial ring, or yeah. So more formally, what we want to have all polynomials in the entries of these sigma that have this invariance property. and that vanish for symmetric on the subspace of symmetric tuples. That's what we want. Okay, how to get all of them? There are two steps to this. The first step is we can actually reduce this problem from, this is a problem about the general linear group of invertible matrices. But we can reduce this problem to a problem that only involves the orthogonal subgroup by decorrelating the signals. So if you look at this covariance matrix at leg 0, it's symmetric, right? We can have this, we can represent it in this way. So if you now define a new process, y of t, in this way, then if you look at the covariance matrix of y, leg 0, it's an identity matrix. So we have this transformation removes the instantaneous correlations in X. Yeah? And so this new process, this decorrelated process, has also a covariance tuple. But now it starts at 1, right? Because at 0 we just have the identity, we throw it away. And we now look at this vector space of these tuples and this linear subspace of symmetric tuples. Now we can restate the problem. Well, first two effects which you can prove is that invariant polynomials under this action of the general linear group, they correspond to invariant polynomials under the corresponding action of the orthogonal group. And this transformation also maps the symmetric subspace to the symmetric subspace. And from this it follows that what we want is this. All functions in the polynomial ring in omega that are invariant and that vanish on linear subspaces. So that now we have a clear what we want mathematically. And now it's also clear why we restrict to polynomials, because there's a very well-developed theory for this kind of invariance. So, and that very briefly is like, so if we look at in this polynomial ring, if we look at all functions that are invariant, these form a subring, and that's called the invariant ring. And the O stands for orthogonal. And there's a fundamental theorem that says that all invariant polynomials are generated by trace polynomials. And what it means is that so all invariants are traces of products of omegas and omega transposes. All of them. That means that you can generate all invariants by taking polynomial combinations of these trace polynomials. And here's an explicit example. So if you have just bivariate signals, and it's 2, then the invariant ring is generated by these trace polynomials, these things. So here the trace of the covariance at leg P, trace of the covariance at leg P and Q, and so on. But in particular, you notice here that you only have to take up to products of 3 different latencies to get everything. This is not trivial. This is a deep theorem mathematically. So we just use it. What I do is kind of trivial. We just use the deep results from invariant theory. And
so sorry, where are the B, Q, and R things? Where are they referring to?
Oh, sorry. These refer to these indices. So the lag at which you consider the omega. So yeah. Okay, so but that's not all what we want, because we also want these functions to vanish on the subspace of symmetric tuples. Yeah, so not all of these invariant polynomials are non-equilibrium measures. Our contribution is kind of to realize that the set of invariant polynomials that are also non-equilibrium measures, they form an ideal in this ring, and an ideal is a generalization of a linear subspace. So it means that so there's a basis meaning a finite number of elements in here, such that every other element in here can be written as a linear combination of these with coefficients from this invariant ring. And there's a very powerful computational method called Krupner basis to find very nice bases for ideals in general. So what we did is apply Krupner basis, just a software package in Magma, to find a nice basis for this ideal. And then we get all other invariant non-equilibrium measures can be generated from these basis elements. So then we get all of them. So if you restrict to 2 legs, so you say I want all non-equilibrium measures, invariant non-equilibrium measures that depends only on 2 different legs of the covariance function P and Q, then we have only 3. So this ideal is spanned by 3 polynomials, and these are these ones. And this is actually the measure that see here. See what happens here. That if the system is in equilibrium, then these omegas are symmetric. So omega q transpose is omega q, and this measure is 0 then. And in the same way, you can see that these 2 measures also vanishes if the omega is symmetric. And all of them we can build by these. Just some general comments. So this measure is a second degree polynomial in the entries of omega. And it is symmetric. So if I interchange P and Q, you get the same. And mu is a 3rd degree polynomial and is not symmetric. So actually, another general comment is that these are also functional connectivity measures. So you can use this potentially to kind of have a directed, this is actually a directed connectivity measure that is invariant to volume conduction. We did not do any calculations for larger than 3 legs, but in principle you can do it computationally. And then just have a brief application. So I applied this to some EcoG data. So we had some EcoG data from a macaque monkey in 2 different conditions. So general anesthesia either induced by ketamine or by propofol. And so here you see the left cortical hemisphere is covered by these electrodes. And I looked at high frequency activity, beta gamma band. And I just calculated this measure, this mu, as a function of P and Q. So you have legs P, legs Q. So you get a matrix. And here you see this matrix. For example, in the ketamine condition, you have P and Q. And this is then how reproducible this. I looked at 2 different sessions. And here you see that there are systematic differences between these 2 sessions. So from this, I deduce that the non-equilibrium dynamics, the structure of that is a bit different in these 2 conditions. Whether you find it interesting or not, I don't know. But that's how you can use this. This is just describe an algebraic framework to systematically derive invariant non-equilibrium measures. And for Gaussian systems, yeah, then you have everything you can have. Because Gaussian systems are determined by second-order statistics. But of course, for non-Gaussian systems, you can look at higher order moment tensors that contain additional information. And we did some explicit calculations in the case of 2 signals. For n is larger than 2, you can do the same computationally. Only for non-Gaussian systems, yeah, what I said, these high order moment tensors, they contain additional information. But to derive those, you have to look at the invariant theory of tensors. So that we cannot do with this, to generalize this. Okay, thanks.